Hello, this experiment is about preparing the optically active isomer tris ethylene diamine cobalt uh, by first preparing the racemic mixture, and we will start by introducing you to the optically active compounds. For example, if you take the chiral center in organic compounds with different groups on around the carbon, you will see this compound on the left has a mirror image on the right, which is non-superimposable. Any chiral center with, for example, this is lactic acid. Any chiral center will have a non-superimposable mirror image. If you lift the picture on the right and superimpose it on the left, it will not impose. For example, like the left hand and right hand, they are non-superimposable mirror images. That's why they call it chiral, which means the left hand is a mirror image of the right hand. But if you superimpose them on top of each other, they don't superimpose. This is the first part of the experiment, and the optical activity is a general phenomena, and we can find it in any more than one type of organic molecules. If any compound, whether organic or inorganic, have a non-superimposable mirror image, that means it's optically active, and they are classified as right-handed and left-handed isomers, or as they call them, enantiomers. For example, tetrahedral inorganic compounds resolved into enantiomers, optically active, and octahedral transition metal compounds, like the one we're going to prepare, also optically active. The compound we are going to prepare is tris ethylene diamine cobalt 3 plus. As you know, we always start with cobalt 2 plus, because cobalt 2 plus is labile and cobalt 3 plus is inert. And after we prepare the compound tris ethylene diamine cobalt 3 plus, we're going to resolve the enantiomers to the plus isomer and the minus isomer. These are the isomers of the tris cobalt ethylene diamine. Now, the isomer on the left is a non-superimposable mirror image with the one on the right. Now, the plus isomer or plus enantiomer, the D dextrorotary, is on the left, and it's the lambda isomer. The structure was determined by X-ray crystallography. So the lambda isomer, which has the ethylene diamine in the equatorial position and towards us, and the other enantiomer, which is the minus enantiomer, is the delta enantiomer, which has the ethylene diamine on the equatorial position facing to the other ethylene diamine with the other isomer, and each enantiomer rotates the light, the polarized light, to opposite direction. For example, the one which rotates the polarized light to the right is called dextrorotary, or D, and the one which rotates the polarized light to the left is called L, or levorotary. The polarized light we use in this experiment is a sodium lamp with a wavelength 589.3 nanometer, and the instrument is called polarimeter. Now, the polarimeter is a simple instrument, contains a sodium lamp, gives a wavelength 589.3 nanometer with a polarizer. So we chop off one component of the electromagnetic light, and we end up with one component or a plane. The plane polarized light, if on the screen, looks, for example, a vertical line with 0 degrees centigrade. If you put an optically active compound which interacts with the polarized light and rotates the light, for example, to the left, the plane rotates to the left, and when you look at the light in the old instruments, we used to adjust the plane until we see the light, and the angle of rotation can be measured. This is the plane drawn on the left here, rotated theta degrees to see the light, and it will give you theta, how much the optically active compound rotated the light, and the measurement is called alpha. Now, if you want to calculate alpha lambda, which is lambda in lambda 589.3 nanometers, alpha lambda, the reported or tabulated values, equals alpha, the measured value, divided by c. B, the length, and c is the concentration in gram per liter, the length in decimeter. So this measurement will give you, for example, plus 89. The values for this complex is plus 89 degrees for the plus isomer, minus 89 for the minus isomer. There is another value which measures the interaction of the optically active complex on the molecular level with the polarized light. It's called M lambda, where lambda is the same, 589.3 degrees. And to calculate M lambda for your complex, you multiply alpha lambda, you calculated up here, you multiply alpha lambda by the molecular weight of the sample divided by 100. It will give you the molecular rotation, which is a relative measure of the rotary power of the complex on the molecular basis. Now, the rotary power varies with wavelength. Here we have one single wavelength, but we have instruments which scans the rotation of any optically active enantiomer with wavelength and gives you M lambda with wavelength. It's called optical rotary dispersion instrument, or it gives you an optical rotary dispersion curve. For example, if you put the plus isomer on this minimum value and goes up to maximum value at around 550 and start going down to the value we measured at 589, which is the sodium value. It's for M lambda, it's about 960, 970 degrees. Now the minus isomer is in the blue line. The minus isomer is 180 degrees opposite the plus isomer. So the minimum on the plus isomer accompanies a maximum on the minus isomer, and the maximum on the plus isomer accompanied by the minimum on the minus isomer, and the minus isomer gives M lambda value of minus 960 degrees. It's worth noting that the plus enantiomer was not separated really, or was not assigned a real structure separate from the minus isomer. So it was random. You give the plus isomer structure and the minus isomer structure. It was not known which structure for the plus and which is for the minus until the 1950s, when the X-ray structure was determined and the delta isomer was assigned to the minus enantiomer, and the lambda structure was assigned to the plus enantiomer. Now, the optical activity or the optically active compounds are very important in the organic compounds, especially the drugs or the medications used, because in the enzyme reactions, the optical activity is important to the drug to be active. The objective of this experiment is to prepare the tris cobalt ethylene diamine from ethylene diamine HCl and cobalt 2, as you know, because cobalt 2 is labile. So we mix cobalt chloride hexahydrate with ethylene diamine in a cooled solution to obtain cobalt ethylene diamine and cobalt in the +2 state. Then we oxidize the cobalt, either by aeration or by adding hydrogen peroxide to convert the cobalt 2 plus ethylene diamine to the cobalt 3 plus stable ethylene diamine. Now we obtain the COEN3Cl3 half NaCl3H2O molecule as a racemic mixture. The next step will be to resolve the complex into the plus enantiomer and the minus enantiomer. Now we proceed to the resolution or resolving the racemic mixture we prepare, the tris cobalt 3 plus ethylene diamine chloride. This is a very tricky reaction. We use as a counter ion an optically active organic substance, which is the plus tartarate. The structure is shown here. Now the plus, we mix it with the racemic mixture we prepared, and we obtain a solid, which is the plus isomer with the plus tartarate, and the minus isomer with the plus tartarate stays in solution. So we take advantage of this property that the minus isomer stays soluble and the plus isomer precipitates. So now we separated the plus isomer as a solid salt with tartarate, and the minus isomer stayed in solution. This slide shows the reaction between the plus tartarate, which carries a negative charge, and we use it as a counter ion, with the complex we prepared, which is the plus tris cobalt ethylene diamine and the minus isomer cobalt ethylene diamine mixed together. Now when we react them with the plus tartarate, it will work as a counter ion, as we said, and the plus isomer with the plus tartarate forms a solid complex, while the minus cobalt ethylene diamine isomer with the plus tartarate stays soluble in solution. Now you filter this mixture, and the solid stays on the filter paper, which is the plus isomer with the plus tartarate, and the other isomer stays in solution. Make sure to clean the Buchner flask, because you're gonna use the solution of the minus enantiomer to precipitate it as an iodide salt. So you take the solution and you add iodide and you precipitate the minus isomer with iodide. Also, at later stage, you convert the plus isomer plus tartarate to iodide salt. So you have three solids now to take the measurements for, which is the plus tartarate with plus cobalt ethylene diamine, plus cobalt ethylene diamine with iodide, and minus cobalt ethylene diamine with iodide. Then you proceed to measuring the optical rotation. Now for the experimental part, you have two alternatives: whether you follow the procedure in this experiment as written. You put 12 grams of cobalt chloride hexahydrate, of course it's cobalt 2 plus, and 13.3 times 2, 26.6 grams of ethylene diamine, each separate until now, and stir in a 250 ml beaker, 25 ml water. You stir for a minute or so, and make sure the cobalt dissolves, which is separate, and you put the cobalt and you dissolve it before you start the reaction. Then you add 8 grams of sodium hydroxide pellets, solid pellets, and 20 ml 3% hydrogen peroxide to oxidize the cobalt 2 to cobalt 3. The alternative, which I sent you by video, it's the link is on your retage. It uses a similar procedure to some extent, 9 mil cooled anhydrous ethylene diamine, chilled to avoid the fuming, because ethylene diamine fumes, and you add 8.5 mil HCl, 6 molar HCl on one side in a separate beaker, 100 ml beaker for example. Then you dissolve 12 grams cobalt chloride 6H2O in another beaker. You make sure that the cobalt chloride dissolves and the solution is clear, and you mix. Then after a while you oxidize the mixture, the cobalt ethylene diamine, with 30% hydrogen peroxide, total of 10 ml. You add drop by drop on a cooled solution to avoid bubbling the solution out of the beaker. Now the resolution of ethylene diamine experimentally, you add 6 grams or the amount you have cobalt ethylene diamine. You make ratios. If you have less than the amount here, you make a ratio. How much do you add tartaric acid? 2.6 grams tartaric acid to each 6 grams of complex, and you put the stirring bar in 100 ml beaker, and you add 20 ml water and adjust the quantities for the amount of cobalt. Then you add 1.4 gram sodium hydroxide, cover the beaker with watch glass, gently stir the mixture and heat on the hot plate for a few minutes until the solids completely dissolve. Then you remove the stirring bar with a magnet and let the solution cool to room temperature. Then if you leave it for more than 24 hours, you can stop the reaction and you come back to it the next day. After 24 hours, you collect the parallel shaped dark orange crystals, and these will be the plus isomer, and the minus isomer stays in solution, as we said before. Now, to measure the optical rotation, we have a vessel for the polarimeter. It's a digital polarimeter. You don't have to look at the lens and check the rotation. You measure the first you dissolve 0.5 gram of each of your enantiomers in 10 ml water, and you fill the vessel and you take the measurement. Now, if the measurement exceeds the limit on the polarimeter, you can dilute the solution to 1 to 1 by taking half the solution and adding half water. If the rotation exceeds the limit of the polarimeter. Now the last step, of course, you calculate alpha lambda, which is alpha at 589.3. The last step, you take one of these enantiomers, either the plus enantiomer or the minus enantiomer, and you racemize the enantiomer to make a racemic mixture, and you measure the optical rotation it should be 0 theoretically. You take 1 gram of your sample, whether the plus or the minus, either or, and add small amount of charcoal as a catalyst and boil the solution 30 minutes, then filter while hot and add few grams of sodium iodide in the precipitation of the racemate mixture. Wash and always wash with ethanol. You will get the racemic mixture and you record the optical rotation. It should be 0. Now the report should contain the percentage yields of all your products, the racemic product you obtained at the beginning, then the plus isomer, then the minus isomer, the optical rotation of the plus enantiomer and the minus enantiomer, the tartarate salt and the iodide salt. So you have alpha lambda for the plus tartarate plus cobalt ethylene diamine plus cobalt ethylene diamine plus iodide, and the minus cobalt ethylene diamine. You measure and you also calculate M or the molecular rotation by multiplying with the molecular weight of your sample. Now you measure, now you have the theoretical value is 89. You divide your optical rotation, for example, you got 75, 80 by 89 times 100%, you get the optical purity of your complex. Then the last thing you do before you have at some stage answer these questions and send them to me. The first question, you plot the ORD for the minus, which I did, and the second question, resolve, and if you have to resolve an unknown complex, how would you know whether or not your resolved products were optically pure? Draw structure of geometrical and optical isomers of cobalt glycinate, which you prepared in the acetyl acetone and copper glycinate experiment. It's similar. Then question 4, why is it not possible to resolve cobalt ethylene diamine 2 plus? The one we have here is 3 plus. Why it's not possible to resolve the 2 plus? Fifth question, draw the structure of the isomers of cobalt EDTA, and in the preparation of cobalt ethylene diamine, what is the purpose of the hydrogen peroxide? بعدين in the purification of both plus and minus cobalt ethylene diamine iodide complexes, the compounds were washed with water containing sodium iodide. Why? Question 8, outline methods for analyzing the plus cobalt ethylene diamine iodide for cobalt and iodide. Look for method. How do you analyze for cobalt? How do you analyze for iodide? Then the optically active tris oxalato complex CR C2O4 3 minus racemizes faster than it exchanges oxalate with free C2O4 in solution. The chromium oxalate enantiomers, they racemize quickly and they use carbon 14 labeled oxalate in solution. Postulate a mechanism. You can, to answer question 9, you can go to chapter 12, the end of chapter 12 in Miesler. It shows the racemization of the complexes and the mechanism of racemization. And that will conclude how to prepare and resolve cobalt ethylene diamine complexes. Thank you.